now that we've got our nscope data into Python by opening the CSV file and saving the data into lists, let's do some analysis where we loop through every point of data that we have and try to find the peaks so that we can count how many peaks there are in our sample and divide by the sample time to guess at our beats per minute. So let's just take an example. We've got some sine wave-ish style data. And you can either try to find the peaks at the top or the peaks at the bottom. So let me describe how we would try to find the peaks at the bottom. Well, if we zoom in on some of this data, we see that we've got data points coming around like this. And if we compare this value to this value and get their slope, this slope would be a negative slope. And if we look at, say, this data point to this data point, that would be a negative slope. And this data point to this data point, that would be a positive slope. So what we're looking for is, when does the slope change from a negative slope to a positive slope? That will give us the point of transition from the data going down to the data going up. So we will have a for loop where we loop through all the data points, and we'll compare this data point minus this data point to this data point minus this data point. And we'd see that there is a negative slope and a negative slope, so we wouldn't keep that point. And eventually we'd get to this data point, and we'd compare this one to this one, see that it's a negative slope, this one to this one, that we have a positive slope. And when we would record this data point, its value, and its time in a new list. Let me show you some examples. Here's some data that I collected from my nscope. And there's just a lot of data. So the first thing I did was I subsampled. I ran through all of the data points that I had and only kept every 10th data point. So this is every 10th data point, and you can see it doesn't look as fine anymore. It's not as smooth because we're subsampling and the noise is kind of coming back out again. So let's say we zoom in on one of these peaks. Here's just zooming in using the zoom button on one of the figures. You can actually see that one thing that can foil our algorithm for finding a peak is that the noise comes up and down and up and down. So if we don't pay too close attention to that, we could accidentally pick up a lot of peaks here. We're trying to find the global maximum or minimum, not one of these local minimum or maximum. So another thing that we can do in our algorithm is we can say, well, we found this peak at this time. So maybe this is t of 0 because it's the first one we found. And later on, we find that was a negative slope and that was a positive slope. So we keep this one, and we would try to stick that in t of 1. As long as t of 1 minus t of 0 is bigger than some threshold, we will keep t of 1. So I would set this threshold to be at least, say, 0.1 seconds, or maybe more. This would mean we would skip data points if they were closer than 10 hertz. Our heartbeat is never more than 10 hertz. So you can play around with this number. Let's go back to the data again. So here's my algorithm having run. I was looking for data points where the sign of the transition went from negative to positive. I had to seed my initial value with an initial data point. So I gave it 0, 0 as my first data point and said, okay, let's just say that that is the first minimum. And then the next minimum that came after that was here, but not enough time had passed for my time threshold. So the next time we had a little bit of an inflection, it found that data point. And then it skipped over until it found this one, and then it found this one, but it seemed to have missed this one, found these. So I have almost a pretty good representation of all of the minimums, and I've saved their values and the times of those values. But I missed that one. Why did I miss that one? Well, if we zoom in on that particular peak that I missed, there were 2 data points at exactly the same value next to each other. So what I didn't consider in my algorithm was what happens if there's a slope of 0. So you might also want to include in your algorithm what happens if you get 2 data points that are the same value. So if we had we've got a negative slope, then we have a slope of 0, and then we have a positive slope. You could probably figure out how to do that with some kind of if statement. Then the last thing I did was I also drew a line across my data and said that my data point also had to be below this line. So if we go back to the data that I ran on, I drew that line at -1 volt. So the conditions for considering a point to be a global minima were that the slope had to be negative and the next slope had to be positive. The two data points had to be at least 0.1 seconds away from each other, and the overall voltage had to be below -1 volts. So for you, you might have to play around with those numbers. Your voltage might be higher or lower, so the line at which it's either above or below will probably be different. The amount of time between the data points that you consider a valid data point, you could play around with that. And then you can consider trying not to miss this kind of data point by saying, not only does it have to be a negative slope and a positive slope, but it could be a negative slope and a zero slope, or a zero slope and a positive slope. So play around with that. I don't want to give you too many hints, but that this is something that should be a for loop and probably take really only 5 or 6 lines of code.